Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 35, lecture 16, the third and final part of this section on confidence intervals for the difference in means. And these take the form mu1 minus mu2. We're going to talk about the third case here. And this is where we have small sample sizes, again, either N1 or N2s less than 30. And we're going to assume unequal variances and they're unknown. So Welch, this is called the Welch's T-test. And Welch showed that if we have two populations that are normally distributed and have possibly different variances, then t is equal to x bar 1 minus x bar 2 minus mu1 minus mu2 over the square root of s1 squared over n1 plus s2 squared over n2 has a t distribution with nu, you can call it v if you like, but it's nu, the Greek letter nu, degrees of freedom. Or I'm trying to draw nu anyway, where the degrees of freedom is given by this lovely little expression. So we have s1 squared over n1 plus s2 squared over n2 quantity squared. Here, don't forget the square. And then on the bottom we have s1 squared over n1 quantity squared. And I left that square off. Over n minus 1, and then s1 squared over n2 quantity squared over n2 minus 1. Okay? And then we can do the same derivation for, since we know that it's a t distribution, we can use the same type of derivation to find the confidence interval. Negative t naught is less than or equal to our expression and is less than or equal to t naught. That's negative t naught, positive t naught. And we can put the equal sign in there. And if we set that probability to 1 minus alpha, then the confidence interval is going to be given by this expression, x bar 1 minus x bar 2 plus or minus t naught times the square root of s1 squared over n1 plus s2 squared over n2. So this is not a terrible calculation here, but the degrees of freedom make this a little bit cumbersome if you're going to do it by hand, as we'll see. And t naught here is equal to t sub alpha over 2 with new degrees of freedom. So let's do an example here. And we're doing the same example that we did in example 2. We have the same sample sizes of 15 and 12. And the means and the variances are all the same. But now we want to give a 95% confidence interval for mu1 minus mu2, but not assuming that the populations have equal variances. So this first step we need to do is we need to calculate the degrees of freedom, Welch's degrees of freedom. So we have I write out the formula because I need to have that to look at so I can plug in the values. And so this is going to be, in the numerator, I'm going to have 193.21, that's S1 squared. I'll pull down so we can see the values, over 15, and then plus 146.41 over 12. Now, again, please pay attention to whether this is the variance or the standard deviation. In this case, it's S1 squared and S2 squared. So if it were just S, then you'd have to physically square those values. And then this whole thing is squared. And then on the bottom, I have, again, S1 squared, 193.21, divided by 15. Now this quantity is squared, and I divide by n1 minus 1, which is 14. And then I add to that S2 squared, 146.41 over 12, that quantity squared over 13, or 11, 12 minus 1, not plus 1. Okay. And so when we calculate this out, the numerator, I get 629.0816423. We cannot round until we get to the end, and that is the probably the most tedious thing about this. In the denominator, I have 25.3835, 8434. And when I divide this, I get 24.783. And so what we do here is we round down to the previous whole number. So that's 24. That's the safest way to do this. Now, we want a 95% confidence interval. That means that alpha is 0.05, alpha over 2 is 0.025, so we have t of 0.025, and the degrees of freedom are 24, so we need to look this up in our t-table, and so we have just so worked out that 24 is here, and 0.025 is here, so it's 2.064 is our T naught. So this is 2.064. Now we're ready to plug into our formula for the confidence interval. So x bar 1 was 125, x bar 2 was 117. Then we have plus or minus T naught 2.064 square root of 193.21 over 15 plus 146.41 over 12. And when we work this out, we get 8 plus or minus 10.3368, etc. And I'm going to round that to 8 plus or minus 10.3, which is going to give me negative 2.3 and positive 18.3. Okay, so that's my 95% confidence interval. So the interpretation is we are 95% confident that the interval negative 2.3 to positive 18.3 contains the true mean difference between blood pressures, or mean difference in blood pressures between males and females. This is male minus female, using samples of sizes N1 equals 15 males and N2 equals 12 females. Now you know how many males, how many females, and you know that it's male minus female. So notice again that we have 0 in the confidence interval. And the previous, so we're going to compare our confidence intervals. And so remember that when we did the same thing, but we had N1 equals N2 equals 50, then we had a 2.9 to something else. I forget the upper number, but I think it was 13.8. But it was, we did not have, 13.1. That's what it was, 13.1. So when we had a balanced confidence interval, but we had a larger N with the same exact other quantities, we said that they were different. Male and female blood pressures are different. But with these smaller sample sizes and unequal, we see that 0 is in the confidence interval, so we don't see a difference, okay, between the two. Now look at the length of the confidence intervals. For the equal variances, it actually turns out that this is longer, a larger confidence interval, and this is a smaller or more precise confidence interval. It's shorter, it's more conservative, but it's more difficult to calculate, where with equal variances we see that it's easier to calculate. Okay, so those are the three cases that we said we would cover for mu1 minus mu2. Now we're going to look at a special case where we do not have independent populations. We have a dependent population, and we call it paired data. So paired data is obtained when we randomly select n individuals from a population. Okay? This can be people, animals, objects, you name it. Okay? Whatever the population is. And we take 2 measurements on each individual or each member of the population. Okay? So here's an example. Let's say that X is a subject's weight before participating in an exercise program, and Y is the subject's weight 6 weeks after beginning the program. Okay? So we need to know some notation and the general form of this paired data. So you see that we have subject here. Then we have the X value, the Y value, and then D. D is equal to, in this case, we're going to say Y minus X. You could have X minus Y. You just have to specify which you're going to do. And for the first subject, we have subscripts of 1, X1, Y1, D1. And then for subject 2, X2, Y2, D2, down to XN, YN, DN. Okay? So it turns out that D1, D2, up to Dn are IID random variables with mean mu sub d and variance sigma squared sub d. And so the sample variance would be S sub d squared. Okay? And we want to find a confidence interval for mu sub d. So it turns out that getting a confidence interval for mu sub d reduces this to the one sample problem of constructing a confidence interval for a population mean that we studied earlier. Okay? In this text, it was section 7.1. And so we have 2 cases here. We have the case where n is greater than or equal to 30, and in that case we will use z, okay, z naught. And then we have the second case where n is smaller, and we will use T naught with n minus 1 degrees of freedom. So much simpler than the Welchs T-test here. Okay. All right. So we have some quantities, S sub d. Okay. So I said S sub d. So S sub d squared is going to be the computational formula is n times sum of d squared minus sum of d quantity squared over n times n minus 1. Some people use the formula, sum of d squared minus 1 over n sum of d quantity squared over n minus 1, I believe. So let's see, that would be, yes. So that's another form of the same equation. So either one of those is fine. I'm used to this one here. So I like it because I'm not putting any fractions on the top or the bottom. It's just multiplying and squaring and what have you. Okay. Now, d bar is going to be the sum of d divided by n. Okay, so the sum of the differences divided by n. So our example that we're going to work is going to be, we're going to have n equals 8. So it's going to be case number 2. We're not going to do case number 1 as an example. Very easy, I believe. But we'll go do case number 2, and so we're going to use this formula, and we have the reaction time of the same subject for red and green lights. So we're calling red X and green Y, and we're going to subtract green minus Y. And we want to know if there is a difference between these reaction times. And you'll notice that all except for one observation is positive, so it would seem like the reaction time for green is actually slower than it is for red. That's what we would think. So let's see what we get. We want to find a 95% confidence interval for mu sub d, and this means we're going to use the formula d bar plus or minus T naught S sub d square root of n. So we have some calculations to do. So n is equal to 8. D bar is the sum of d divided by n. I've summed these up. It is 0.50. And so we get 0.0625. And I'm going to keep those decimal places for now. And then we have S sub d squared. Again, n times the sum of d squared minus the sum of d, quantity squared, over n times n minus 1. So I didn't show the calculations, but I added up the squares. So use 0.13 squared, 0.09 squared, and you add those up, and this is the sum of D squared. Okay, so you have to square the individual values, then add them up. There's no shortcut, so please don't try to take one. It doesn't work. Okay, so 0.0722 was the exact value, so it's 8 times that minus 0.5 quantity squared over 8 times 7, which is 56, and we get a value of 0.00585. So that's the exact value. We cannot round this. Okay, we cannot round anything until we're finished with our computation. So S sub D is the square root of this. It would be easier actually to write the square root of 0.00585, and I was tempted to do so, but I wanted to write out all the decimal places so that I could emphasize do not round, or you might get the wrong answer. So S sub D is, in my calculator, I get all those digits. Next thing we need to do is we need to find T naught. So T naught is going to be T sub alpha over 2 and n minus 1 degrees of freedom. N is 8, so we have 7 degrees of freedom. Our C is 95, so alpha equals 1 minus C is 1 minus 0.95 equals 0.05, and alpha over 2 is 0.05 divided by 2, or 0.0250, if you like, but I don't need the O for the T. They only have 3. Okay, so I look up T of 0.025 and 7 in the T table. So get rid of our previous scribbling. So I need 0.025 and 7 degrees of freedom, and I get 2.365. 2.365. And so T naught is 2.365. Now I plug into my equation. So I have, this is D bar plus or minus, I've written it up here. There we go. So I don't need to rewrite it. Oops, wrong erase. There we go. Okay, so I've got 0.0625 plus or minus T naught 2.365 times my S sub D, this is S sub D, divided by the square root of n, which is the square root of 8. And when I calculate this out, I get 0.0625 plus or minus 0.0640. So, yes, again, don't round until here. And I did this to too many decimal places. I should have done this to 3 decimal places, but I went ahead and did it to 4. So when we subtract, we get negative 0.0015, and when we add, we get 0.1265. Notice again that 0 is in the confidence interval, and that means that there is no difference at 95% confidence level. There's no difference between the reaction to red lights and green lights within the same individual. So let's write it up. This is a little more difficult to write up because we need to describe what we measured, the mean of what. So we are 95% confident that the interval, there's our interval, contains the true mean difference in reaction times for green and red, green minus red, lights for the same individual using a random sample of size n equals 8, and I made sure that I said paired observations. So it's very obvious that these are paired observations. Okay, so that is how we do paired differences. So we've done case 3 of mu1 minus mu2, where the variances are unequal, and we used Welch's T-test, and we did the paired T-test, so for paired samples. If you have questions, please come to virtual office hours. If you need help before you get to virtual office hours, before you can make it, then by all means email me, but make sure that you email me a picture of the problem, because I may not have it available, and a picture of your work so far so I can see how you're approaching it. And then I'll be able to help you more thoroughly and quicker by doing that. So please take care of yourself and stay safe. We want to see you here next time.